example. In this case, this is a problem that's out of the problem section of Boranaki's book. This is problem 459, where we have a condenser, a heat exchanger, that brings 1 kilogram per second of water flow at 10 kilopascals and has a quality of 95% steam to a saturated liquid. So it's changing it to a saturated liquid at 10 kilopascals, so it hasn't changed any pressure. As shown in this figure, the cooling is done by lake water at 20 degrees Celsius, and it returns to the lake at 30 degrees Celsius. It makes the fish all happy that they did that. This is an insulated condenser. We want to find the flow of the cooling water. So a basic heat exchanger problem, one that you should feel pretty comfortable doing, and you'll do this again in when you take heat transfer. So what did I decide to call these things? I guess I decided to call this WTR, and that was the 1 kilogram per second. It says it right there. Pressure at 1 is 10 kilopascals. So here's 1 to 2. So that's going to be the same right here from right to here. So I got to find out these properties. So I need to go to a table. So I go to table B.1.2 because I'm using 10 kilopascals. So at 10 kPa, the temperature I didn't bother to write down. So that's the kind of person I am. So we went to HF was equal to 191.81 kilojoules per kilogram, and HFG was 2,392.82 kilojoules per kilogram. So I found what my H1 is going to be HF plus X times HFG. So 191.81 plus 0.95, 2,392.82. A lot of decimal places and stuff there. 2,465.0 kilojoules per kilogram. And then, so they said that they wanted to cool it down, so it's a saturated liquid. So H2 is just going to be HF, which is 191.81. So that was our goal. We're going to find how much water. We can also look up, and just to make my life easier, when it's just going to be water and they don't know anything about the pressure, there's a good chance that you could just go ahead and look up the, especially if it's just water. It's not changing phase, nothing. Go to table A4, and for water, find the specific heat. And we can use that. So when it comes to a heat exchanger, right? I'll write it out. Boom. Well, nah. Yeah, I guess I'll do it. Okay, I'm sorry. Minus, I was getting lazy. Summation of m dot in minus summation m dot exit h exit. We're going to say that the thing is insulated. There's no work done onto the thing. So we're going to have all of the in mass times the enthalpies of the ins, mass times the enthalpies of the out. So we're going to have m dot water coming in times its enthalpy 1 plus m dot lake H3, right? So there's 3 coming in. So that's coming 3 coming in, 1 coming in. Now we have m dot water H2. It's exiting. Minus m dot lake H4. So bring them all together. M dot water, sure, H1 minus H2 equal to M dot lake. Gotta be careful here because I want to keep my signs correctly. I think it's going to H4 minus H3. But I have an option here. I could also go M dot water. I guess I could start entering in numbers right now, I think. But M dot lake is what we really want to try to get. We can go CP and then go T4 minus T3. All right, so we could put this numbers that we have 1 kilogram per second. H1 was 2,465 minus H2 was 191.81 equal, this is what we want to find, the amount of flow of lake water. CP is 4.18, and our temperature change is going to go from, so it was exiting 30, entering at 20. And so everything works out. And we get that 54.38 kilograms per second. And so that is our answer. It's pretty handy, this equation right here. I did on my page a shortcut where I just went like Q dot equals Q dot, which is basically this is Q dot and this is Q dot right there, and I just right here. But I think it's better to have just one equation, not to have to memorize stuff, or when to use it, when not to use it. Just kind of think and just think your way through the scenarios. On to the next.